Hello. Now I want to make an introduction, and before jumping into the specific topics of the analysis class, I want to repeat what we learned so far. So we start from the statics. Let us very briefly try to remember what we learned. Starting point in statics is actually the equation of motion. Very simple equation. Force is equal to mass times acceleration. F equals ma. And this formula is for a particle. What this means is when you apply force, it just simply moves. Wherever the direction of force is, it just simply moves. The point is not a structure because its dimension is zero. But when I add another dimension, not a zero dimension now, but one dimensional member, and our dimension has a length of L, let's say. Let's say that this is the center of gravity. Let's let's apply a force. Let's apply a force here. In order to describe that motion, we need a coordinate system. Cartesian coordinate system, x and y. Divide the motion into three components. Divide the motion into three components. First component is in the x direction, right? I mean, I know that it doesn't translate. I'm just writing the very general terms. It moves this way. Translation in x direction. Plus, of course, translation in y. This is the final destination of the beam, the same beam. And there is a rotation, right? Rotation about the center of gravity, right? In rotational motion, we don't have any translation. The member rotates along the center of gravity, and that's the rotational motion. Basically, with these three components, we can describe any type of motion of a rigid body. This is rotation, and this is translation in y, right? Now, how can I write the equilibrium equations? Dynamic equilibrium equations for each case. So for the first case, we say that the sum of the forces, all the applied forces in the x direction is equal to mass of the body times the acceleration in the x direction. Likewise, in order to figure out the motion in the y direction, or write the dynamic equilibrium equation, we say that sum of forces in y must be equal to mass times acceleration in the y. Mass times acceleration in the y direction. This is of course x. But also we have a rotation, and as you see, if you go back to this force, take a look at that figure right here, right here. This F will create a rotation motion because it's not directly applied to the center of gravity. So we call the rotating effect of any force by moment. So the sum of moment in this element must be equal to the mass moment of inertia multiplied by rotational or the angular acceleration. So these are the dynamic equilibrium equations that we can have for a member two-dimensional space. But in statics, we simplify it because for most our case, we don't want our structure to move. So we say that under any given applied forces, if we don't want our structure to move, we say that acceleration must be equal to 0. Translational acceleration plus the angular acceleration. So this is the static condition that we have. We say that no acceleration. So by using that, we say that for a system to be in static equilibrium, if we are examining the structure in two-dimensional plane, we must have total sum of the forces anywhere in the structure must be equal to 0. Sum of forces in the x direction must be equal to 0. And of course, sum of forces in the y direction again must be equal to 0. And these equations must hold anywhere at any point in the structure, and sum of moments must be equal to 0. So this gives us free equilibrium equations. So if I have three-dimensional structure, what if I want to analyze the structure in 3 dimensions? Then I will have 3 translational components. Sum of forces in x direction is 0. Sum of forces in y direction is 0. So these are all the translational motions, equations related to the translational motions, and we have equations related to the rotating motions. In 3 dimension we have 6 equilibrium equations. And if you think about it, in statics, this is what we do. We had 3 equations and we try to analyze different types of structures. So now let's take a simple support of P. And I apply force at the middle. Let's give some numbers. Let's say that 10 kilonewtons and 2 meters. Okay, so when I look at that structure, how many unknowns do I have? That's what we are doing in statics. So one unknown is this support reaction, because remember that we define a pin support. We say that this point cannot move in x and y directions, and it's supported by this pin support, and we have 2 reaction forces here. Let's call it A and B here. So I have AX and AY, and here is a roller support, meaning that it can only resist translation in the vertical direction with the help of a support reaction. Let's call it BY. Okay, when I look at that structure, I got 3 unknown support reactions. Okay, and this is we are solving the structure 2 dimensions. So I got 3 equilibrium equations, and what I learned here is I got 3 unknowns and 3 equilibrium equations. So our conclusion is we can determine all the forces, we can determine all the support reactions, and internal member forces using equilibrium equations. So we call this type of structures as determinate structures. Why? Because I can determine all the forces by just using equilibrium equations. So it's determinate. I can determine it, right? But remember, this is of course the mathematical definition of the system, or mechanical definition. Now let's take a look at the behavior. How does the determinate structure behave? Now remember that these are the minimum requirements for stability. What do you understand the stability? Having free support condition for stability. What will happen if I remove this roller support? How does the structure move? Remember, I don't have any resistance. I don't have any enough resistance to avoid motion in the structure. If I remove that support B, it will start to rotate, and this structure will no longer be in static equilibrium. It will move, okay? So the minimum condition for a 2D structure is to have at least 3 unknown support conditions, okay? So if you don't satisfy this 3 support reaction condition, you have, of course, in terms of statics, we say that your structure loses its stability and it will collapse. The other property of a determined structure is as follows. Let's say that I have these 3 structures. The first one is I have a very thin member. In the second case, I put a very strong member. And in the third case, let's have something random shape beam here, and again pin supported. All of them pin supported. And for these 3 cases, I apply the same loading, 10 kilonewtons at the middles. What do I find as my support reaction in 3 of cases? They are always the same. So the shape, whether it's a metal or a wood, doesn't matter. We always have the same support reactions, right? The same internal forces, because the force distribution depends on equilibrium equations. These 3 equations, nothing else. And if you look at these equations, we don't have the sectional properties. We don't have the material properties in these equations. So actually, the force distribution or the support reactions is determined by these 3 equilibrium equations. Now, let's add another span. Now, let's consider a continuous beam. Alright, I have a fixed support at A, and I have a roller support B and C at B and C. I had another span between B and C. Let's say that the second span is 4 meters away, and this is 2 meters, and this is 2 meters. 10 kilonewtons applied at the middle of A and B. This time, let's take a support reactions. This is AX, no, this is AY, and AX, actually it doesn't matter, never mind. This is BY, and this is CY. In that case, what do I have? I got 4 unknown support reactions but the number of equilibrium equations, they don't change because it's a two-dimensional plane, and two-dimensional plane we only have three equilibrium equations. Alright, by using the three equilibrium equations, I cannot determine the unknown support reactions. So our conclusion is, by using equilibrium equations, we cannot determine the unknown support reactions. So, if you don't determine the unknown support reactions, we cannot calculate the internal moments. Or we cannot calculate the deflections. We don't. So, this type of structures, we call it indeterminate structures. Right? By using the equilibrium equations, we cannot determine all the unknowns. So, what do we do? What do we do? Ooh, I need additional equations. Okay? So, we need additional equations. So, what else do I know about these structures? Now, related to the forces, I have only the equilibrium equations now. I'll take a look at the deflections or the deformations. What additional information do I have? I have a pin support at A, right? Here. So the deflection here is equal to 0 in the X and Y direction. Likewise, at B, deflection is 0 again. And at C, the deflection is equal to 0. So, let's sketch the deformed shape. Probably it will deform like that, the green shape. But the condition here is 0. Delta yb is equal to 0. Delta yc is equal to 0. And likewise, delta c, delta a, delta ya is equal to 0. So these are the conditions, these are the additional informations that I have at the structure. So what do we call these additional informations? Information related to deformations, they are called the compatibility equations. Right? The equations related to the geometry or the deformations of the structure. Equations that describe the deformation of the structure. Okay, now I have this information. Delta yb is equal 0, and that information, delta yc is equal to 0. And also I have the equilibrium equations. So the question is, how do we combine the compatibility equations with equilibrium equations? That's the main question. If we can find a way, we can actually analyze any type of structure, whether it is determinate or indeterminate. But of course, the other thing that I need right now is, how can I describe the formation of a structure? How does a structure deform? That's the question we are asking ourselves, because we need that information to analyze any type of structure. So that we learn in mechanics of materials, because in statics we can only use equilibrium equations. We can only analyze determinate structures. And here, what we saw that in order to analyze indeterminate structure, we need additional information and information related to the deformation. So, how does a structure deform? That's the question we're asking. Mechanics of materials, how members deform? This is mainly what we focused on in 224. And we try to relate deformation with internal forces, but of course, when we say mechanics of materials, it's a very wide topic. We are limited. We say that we're only looking at the solids. The other issue is the only elastic material, and we assume small deformations. These are our limitations of our discussions in the mechanics of materials. We say these are the limits and basic assumptions. Now, we separate the behavior of a structure as actions, and we have the effects. So that's the main simplification we have. Okay, we have some actions of a structure, and we see the reactions, and now the action for us are loadings, right? We have point loads, we have uniformly distributed loads, we have moments, we have thermal effects, and so on. So these are all external effects. We classify them as our actions, okay? And when you load a structure, it has a response. The response is as a deformation. That's the approach. You load a structure, you get a response. The response is the deformation. This is the deformation, something that we can measure, we can visually see. But the deformation is really very complicated for us again. So we simplify it. So we classify the deformation in 4 sections. The first section is the axial deformation. The second one, these are all the chapters of the mechanics of materials. You first examine the axial deformation, and then you examine the torsional deformation, and then flexural or bending deformation, and finally examine the shear deformation. Okay, so our approach was as follows. We have an action, a load. So let's take a look at it. Draw a simple figure. I have a load on the structure. So what does it cause, that load? That load causes a moment. in the structure. So we draw a moment diagram, right? That's the moment. And because of that moment, internal moment, we see deformation in the structure. So the internal forces, the stresses due to that internal forces, they are all abstracting. They don't exist. What really exists is the deformation. But we use these internal forces, stresses, to relate the external effects with the deformation. Okay? So how do we do that? And in most of our derivation, we take a complex structure again. This is a simply supported beam, and then from that element we take a very small piece. We call it infinitesimal element, depending whether we are doing a formulation one dimension or two dimensions. The shape of the infinitesimal element change. So we can take an infinitesimal element. Let's exaggerate it. I have an infinitesimal element whose dimensions are, if it's one dimension, it's dx. If it's two dimensions, we have dx and dy. And we have some forces on it. So we no longer call the force on a dx infinitesimal as force, but we call them stresses. And we have the formation of this infinitesimal element, and again we don't call them deformation. If it's only infinitesimal element, we call them strains. And then we try to relate strain with the stresses and the deformation with the strains, and we do some formulations and we come up with some equations that relates the applied forces with the deformations. So I will not go into details of derivations, but let's focus on the types of the deformations. Types of deformations that we see. So action, and let's show the effect here. I have this square. Let's take a square and apply an axial force, or you can just take a slice from your member, and what you see is the internal axial force on it. Let's call it N. Okay, to imply that that's an internal force. So how did we define the deformation due to axial force? It's by elongation. Initially this was a square, but due to the applied axial force we have a longer member. This is our elongation. If we are writing this on an infinitesimal element, we just use the axial strain. But let's write it in a general way. This is the axial deformation. Convert squares into rectangles. So that's the way we define axial deformation. You have an axial force on your member, and the deformation that it causes, the shape change it causes, is as follows. Now, we can have a flexural deformation. We say that flexural deformation, the flexural deformation is caused by internal moment. Okay? Now, how does it deform? If I have a square, what type of a shape will I get after the application of this moment? We say that it will become a trapezoid, right? Because the moment shortened the top fiber, and will have tensile components of this moment. It tries to elongate bottom fiber, and at the end of the day we have flexural deformation that converts squares into trapezoid. Okay? So how did we describe that deformation? In a very simple way. We will go over it later again, but we just use this angle. This angle. This angle tells us how much deformation we get. And we call this angle as phi, and this is the curvature. So we describe the flexural deformation with curvature. We say that axial force causes axial deformations, moment causes curvature. That's the way we relate the internal forces and the corresponding deformations. We have one more deformation type, but I will not focus on torsion here. Now, this is the internal shear on a member. So, what kind of effect does it cause? So, I have a square element here. So, initially I have a square. So, what will happen if it undergoes shear deformations only? By definition, we say that shear causes angle change. So, initially these angles are 90 degrees, but since we have a shear deformation, they no longer become 90 degrees. They change. So shear deformation converts squares into parallelograms. And the way we describe the shear deformation is this angle change, and we call it shear strain. Alright, now for an infinitesimal element, we can determine how a force, whether an axial moment, change its shape, but what about the member? And also, what about the structures? We briefly We briefly talk about the strength of material cores, actually, but that's the topic of structural analysis. That's all for the intro. See you very soon.